All right, so for next week, lab number 5 is not in your book. It's not in your lecture manual. I will have to provide a copy of you to that. It's just like I did before. I'll be sending you a PDF of that lab, so don't copy the one out of your book, all right? So I'm not using lab 5. Okay, so chapter 8. Have you guys ever seen this out in the ocean, like at night? Have you been walking along the beaches? I don't see it as much in Florida as I used to do in California, but maybe some other areas. You guys know what this is? This is you're walking down the beach at night and see the stars, and what I'm asking about is what is all that blue in the water, that glowing blue? You've ever been on a boat at night, and especially if the seas are relatively calm, as the boat cuts through the water, that wave that it pushes out, you might have seen it happen there too. I remember a lot from when I was in the Navy, being out in the middle of the night in the ocean and cutting through the water, and you'd see sometimes it was blue or green and it would glow like this. You guys have never seen this? There's all sorts of neat, really. Yeah, it's awesome, isn't it? It's beautiful. It's actually take your breath away stunning. There's plenty of videos on YouTube if you haven't had the chance, but honestly, nothing like being in person and seeing. And what's happening here is that there are bacteria in the water, and those bacteria are responding to being agitated. So these are the waves breaking up on the shore. It's kind of like my ship cutting through the water at night, forcing that wave. And when you agitate these bacteria, what they do is they glow. They give off this. They give off light. They give off. Sometimes it's blue colored. Sometimes it's green colored. And there might be other colors out there. Maybe yellow color. I'm not sure. But what they're really doing, what they're essentially doing is trying to freak out predators or get predators confused. Small little predators that would feed on these bacteria or these other smaller organisms. Not just bacteria can do it. Dinoflagellates, which is a protozoan, can do it. What they typically have, though, is they have the bacteria living inside of their tissues, so it's a symbiotic bacteria. But whenever these bacteria get agitated, or the organisms that contains them, this flash of light distracts predators or blinds the predators for a second, at least in that local area. And the idea there is it prevents or kind of freaks the predator out. They lose sight. They can't see the prey that they're going after. But what they're really doing in terms of chemistry is they're doing what chapter 8 is what we're going to talk about in this chapter is metabolism. They're actually engaging in a chemical reaction. And that chemical reaction, in this particular case, is releasing energy. Light is energy, right? And there are 2 basic types of chemical reactions out there along very basic lines. Reactions either release energy, right, like this one, or they absorb energy. I'm sure I'm not saying anything new, but from our discussions about organic molecules and food, that's what food is, a source of energy. You can put food into an oven and turn up the temperature enough that you can get it to catch on fire, right? You can combust it, and that fire is that release of energy coming off that food that you burn. That's the same thing that happens in your body. It doesn't burn like a flame, obviously, but the energy in food is being released. Okay, and that energy that's being released in your food will eventually do things like drive your muscles and get your body to work. But actually, it's kind of like wheels on a watch, geared wheels on a watch. The energy that's released from the food that you eat drives a gear that drives another gear, and then may drive actually several other gears before the final gear is driven, if you understand what I'm saying, right? So sometimes the energy that we absorb in food is not directly transferred to me moving my hands. It's been transferred through a series of processes that releases and stores that energy. And so we'll talk more about that when we get into respiration. But this whole first part is important, this chapter 8, because we can't understand respiration. We can't understand the next chapter, photosynthesis. I mean, to be honest, you can't understand anything about life until you understand what this metabolism is all about. Now, again, this is kind of going back to the first few chapters where we did chemistry. We're linking what's going on in chemistry to how biological things, all right, biological systems, because there are chemical systems, they aren't alive, but there are biological systems as well. Now, those are alive. So we're linking how this chemical system links with this biological system. In other words, how do living organisms survive in a world in which you need energy to survive? Okay, especially if you want to remain a complex thing. And life, no matter, even when we go down to the prokaryotes, is still pretty complex. All right, so let's get a little bit of terminology done first, and then we'll be able to use that as we're going through the rest of our discussions. And I've got some pictures here to give you examples. You might remember from some of your I don't know, science or chemistry or perhaps physics courses that there's two types of energy out there, right? There's the potential energy, and then there's kinetic energy. If you do remember them, do you remember what their definitions were? What was the definition of potential energy or kinetic energy? Anybody remember that? If you think about the word potential, right? What does potential mean? Okay, so potential means that that's something that hasn't been used yet, right? It could happen. There you go, Gavin. Thank you. Yeah, it's something that could happen. It's something by virtue of the way a system is set up that it provides the ability for something to happen. That's why we call it the potential, right? So if you take a look at this, let's look at the dam first. That's usually the one that folks go, what are you talking about? Because that's talking about living things. Well, the water held behind a dam is pushing on that dam, right? There's force being applied to that dam. That's why dams very often, especially modern ones, were kind of, oh, thank you. Oh, drawing on the wrong screen. Oh, shoot, I forgot. Anyway, I'll use this. Dams are built sort of in a semicircle so that the pressure of the water that's pushing on them from behind, the semicircle of the dam, they're also usually built very solidly into the canyon walls. There's a lot of force of that water pushing that dam forward, trying to bust the dam, if you will, okay? So that force that's pushing on that dam is considered potential energy because it has the energy to do something. If the dam broke, it would have the energy to wash downstream and wash everybody's houses and perhaps a lot of people downstream, okay? You know, it would have the potential to erode the river downstream, to carve away at rock. If there's a dam there, if the dam didn't break, and we let the water through, like these little spigots that you see there, what we're doing in that particular case is that potential energy is doing work. It's spinning the turbines inside that dam, which makes electricity. So when the potential to do something is turned into that which is getting done, washing everybody downstream, carving the river, or spinning these turbines, you're converting the potential energy into energy of motion. Kinetic energy. That's what kinetic means. Kinetic is the energy of motion, okay? So what we do in the terms of this whole laws of thermodynamics is we take this ability to do work, right? And we turn it into work. So the guy gassing up his car up above, in the gasoline, by the virtue of the chemical structure of gasoline, there's potential energy there. The way the molecules are linked together, the way the atoms are linked together in gasoline, you can break those bonds, you can do a chemical reaction, you can turn that potential energy into something that actually happens. And the word got erased off the screen, but it should say when he's driving his car, now the car's moving and it's kinetic energy. Now we're going to learn that it's not always efficient though, right? So, for example, the guy with the gallon of gas or the gasoline in his car, I think, if I remember correctly, that the amount of kinetic energy you get out of that gallon of gas, in other words, the amount of energy that actually moves your car from a gallon is only about 30%. So only about 30% of that gallon of that gasoline that you burn in the engine of your car actually makes your car go forward. You know where the other 70% goes? Well, the majority, right? Where does the majority of the energy go? I'll give you a little hint. If you've driven a couple of miles and you get out, say you've driven 10 miles, and you get out and you put your hand on the block of your engine block, what happens? Yeah, it's hot, isn't it? Right? Okay. So, and heat is energy. It's not a particularly efficient form of energy. It's what we call it's what we call sort of disorganized energy. Okay. But it's energy nonetheless. That's where that 70% went. 70% of the gallon of gas. So if you buy $1 worth of gas, which wouldn't give you anywhere near a gallon, of course, 70 cents out of that gallon is used just to make the engine just to make your engine hot. And does your engine hot get you to work, or does the 30% of the car rolling get you to work or to school, right? So it's not a particularly efficient system. None of these systems, the ones you see, are 100% efficient. That's the laws of thermodynamics, and we'll talk about those next. Now, the kid coming down the hill, that's gravitational energy, right? He's up at the top of the hill. He has the potential to roll down the hill. And as he rolls down the hill, that potential energy turns into rolling, which is movement, and kinetic energy. He gets to the bottom of the hill, the guy burns out of the gallon of gas, or you've drained all the water from behind the dam, you no longer have potential energy. It's all converted into kinetic. Make sense? So now when we look at the cheetah, he's got potential energy when he's just kind of laying there looking out across the African plains, thinking about what his next meal is going to be, thinking about where he's going to sleep tonight. Man, I tell you, being a big cat like that would be awesome. Nothing really messes with you. You know, every once in a while you got to deal with battle with other males, you know, and I don't know how often they feed. You are a mammal, but every once in a while you chase down an old limpy gazelle, because you're not going to go after the strong ones. Why do that? Make your life easier. Just to let you know and help you feel sleep better at night, I do some of the data I've seen about predators chasing their prey. I don't remember if it was specific to cheetahs. It might have been, but it said that 80% of all cheetah attacks, 80% of all initiations of an attack on a prey end up in failure. So they miss 80% of the time. So next time you see it on TV, if you're worried about that little gazelle running away, just know that 80% of the time they get away. Okay, so as soon as that cheetah gets up and starts turning that potential energy into energy of motion, that is chasing after that prey or running off wherever they're running, then it turns that energy of potential into kinetic energy, right? Now, since we're finished up with the biological system, let me ask you a question. What would happen if all of the potential energy, kind of like of all the potential energy was gone when the kid rolled downhill? What happens if that cheetah were to run out of all of its potential energy? Same thing would happen to you. Right. Wouldn't be able to move, wouldn't we? Yeah, that's correct. Yeah, we would. If you ran out of, so in other words, translated in other forms, if the cheetah stopped eating, that's it, I'm done, I'm not going to eat ever again, it would die, wouldn't it? Right? There would be no kinetic energy. He wouldn't be able to chase after anything. And down at the cellular level, all these things that we're going to talk about that happen at the cellular level, respiration, and if you're a photosynthesizer, that, and the enzymes that we're going to talk about, and all that sort of stuff, that all needs energy. That's all turning potential energy, food energy, into kinetic energy. Kinetic energy doesn't necessarily just mean the car moving, the cheetah running, the kid rolling downhill. Kinetic energy also means the chemical reactions that are necessary to keep living things alive, all right? Okay, so now that we got this term potential and kinetic out of the way, right? We're all good with that? Let's talk about thermodynamics. The entire world, the universe, everybody, everything, all of it is driven by thermodynamics. It's very simple. What's the answer to the universe? There's two laws. That's the answer to the universe. The first law says that energy can be transferred and transformed, but not destroyed or created. The amount of energy that's in the universe, it's a physics law called the conservation of energy. The amount of energy that's in the universe is constant. Maybe they've measured it. I don't know. They probably estimated it. But if the amount of energy in the universe is X amount of whatevers, however the heck you'd measure something like that, it's been the same from the Big Bang all the way through today. It has never changed the amount of energy. Okay? That's the conservation of energy. That's a law of physics. Now, what that means for living organisms is that bear right there that's ripping that salmon apart. If that bear wants to avoid having no more potential energy, dying, right? He is going to have to get some energy from somewhere. Now, he can't make it. The bear can't make its own energy. Now, wait, I know you're thinking, wait a minute, what about plants? We'll get that in a second. So the bear can't make his own energy. So what? Because that's the first law. You can't violate these laws. You don't get fined. You don't go to jail. You can't violate them. It's like jumping off a building and expecting gravity not to happen. Actually, gravity explains it, or thermodynamics explains gravity. So he has to go get the energy, right? He's got to go out and he's got to eat. He's a heterotroph. He goes out and he hunts and he consumes it, and he brings the energy of that fish into him. And that fish got its energy from whatever it ate, and it got its energy from whatever it ate, and so on and so forth. Now, to answer your question for those that are thinking about plants, plants don't make energy. They make food, but they don't make energy. What plants do is they take the energy from the sun and they convert that into chemical energy. Glucose, remember that molecule, that sugar of choice? That's chemical energy. There's energy, just like that gallon of gas, in the structure of glucose. So where did that energy come from? Sunlight. Plants are able, thank goodness, thank you plants. Plants are able to convert sunlight. They're able to convert, see, we can convert. Energy can be transferred and transformed, but not created or destroyed. Okay, makes sense? Isn't that neat? It's nice to know you have the answers to the entire universe. Well, I got to give you one more law, but all right, now, along with that first law, if we go back to something that we talked about a few chapters ago when it comes to this movement of electrons, okay, because, and I'm introducing this now simply because I want you to have sort of a baseline familiarity, because we're going to come back to this whole electron movement thing, especially when we get into photosynthesis and respiration next few chapters, okay? So we basically got two atoms here, A and B, and we're going to reduce one of them. We're going to oxidize the other one of them. They gotta work together, right? It's called a redox reactions, and you can't have a Re without or reed without an ox. You can't have an ox without a reed. In other words, if you want to get rid of an electron, like remember it had one extra, if you want to get rid of it, you can't just say, go off electron, be gone. You have to give it to something. And if you need an electron, like chlorine, there isn't a pool of electrons like Go Fish by which you can go grab an electron. Remember, that's why those two things got into the relationship, sodium and chlorine. Sodium had an extra one, chlorine needed an extra one. Oh, look at that. It's a yin and yang. You give me your extra one, and oh, guess what? Now we stick together because the charge has changed, right? One of it's positive, one of it's negative. Okay, now, so you understand the positive and negative part. We understand why we call them reduction and oxidation. I want to superimpose that now with the thermodynamic law. What's going on when something has been oxidized is the energy of that material was lowered. All right, see A went from gray to yellow, and down below it says yellow means the energy was lowered. And when something was reduced, the energy is increased. The energy, and A didn't destroy its energy, and B didn't create its energy, it transferred energy. What was transferring the energy between A and B? What was the thing that transferred the energy? What was the thing? What was the actual physical thing that transferred the energy from A to B? A lost, B gained. What did the transferring? Look at what the whole equation is showing you there. Jasmine, what do you think? Amber Hopkins. Yeah, electrons, right? You see how that's working right there? That thing we talked back in the early chapters, look at that. It's transferring electrons. Okay, so the act of transferring electrons, when we talked about that way back in ionic bonds, we only talked about it in the form of creating a positive and negative because we were talking about bonding. That's an ionic bond. But in that process that was going on, what we didn't talk about at the time, and now we are going to talk about it because it's going to become really important in those chapters I just mentioned, is when you move electrons, when you oxidize or reduce things, you're moving energy. You're transferring energy, okay? So keep that in your head and keep that simple little chart that I'm down there in the lower left in your head. When we move on to the chapters, get a little bit hairy. We get into photosynthesis and respiration. All right, so here's Mr. Bear. Now, the second law says that every energy transfer, or every time you transform it, every time an electron moves from A to B, okay, there is the Piper's fee. All right, that's an analogy. Entropy increases, disorder in the system. Okay, just what I was saying about the fellow with his gallon of gas. When the energy is transferred from the gas molecules to the spinning of the wheels of his car, you know, the moving of the pistons, obviously, and all that sort of stuff. When that happens, some of that energy has to be paid to, you know, my dad used to always say when I got in trouble, now, son, you got to pay the piper. You have to pay, you have to give. That's some of the energy that is lost. That's some of the energy just goes off. Now, it's often lost, as you see in this bear, it's lost in heat. So the bear's running after something, you know, maybe a hiker got too close, right? And the bear's respiring. That's the carbon dioxide in the water that's being given off and all that sort of stuff. And it's taking the carbohydrates that it ate when it was in the proteins and the fats that it ate when it was eating that salmon, and it's turning them into bear running. It's turning them into the kinetic energy that's moving the bear forward. But the Piper's fee, or the entropy, is increasing. So that means that the energy is not 100% transformed, and that's lost as heat. And as I said, heat is not a particularly efficient form of energy. You can use it, but it's not the most efficient form of energy. Okay? So you notice in this particular case, before you start thinking, well, the energy got destroyed when the bear was running, remember it didn't. The energy got turned into the energy of movement of the bear moving, and then way getting out of scope. If you think, well, where'd that energy go? Well, that came from his paws hitting the ground, pushing against the dirt, blah, blah, blah. All that is energy. If you don't think pushing your feet against the ground is energy, jump off of a 2-foot stool and then jump off a 30-foot stool. You're still pushing your feet on the ground. You tell me which one has more energy in it, okay? So whenever you do kinetic work, whenever you do any work, whether it's movement or the stuff that's going on inside the bear, you don't get 100% transfer of energy, you see? Now, this has interesting implications in an ecosystem, and that's why I'm throwing that little part down there on the bottom. I don't think I asked you anything on the exam, but I do think it's interesting to think about that. There are more plants in the world than there are what we call tertiary consumers, right? There's plants, there's those that eat the plants, those are consumers, those that eat the things that eat the plants, the herbivores, the carnivores, the herbivores, and then there's the things that maybe eat carnivores and herbivores. What you're seeing in the pyramid, though, is something in ecology, something in environmental science that we call the pyramid of energy. Right? And it's shaped like a pyramid, and J is joules. It's an amount of energy. And notice what's happening as we go up the pyramid. So as the amount of energy that the plants produce when they do photosynthesis, as it gets consumed by the herbivore, then the carnivore that ate it, look how much energy is lost between each level. We say on average in an ecosystem, 90% of the energy to be passed between each levels is lost. That's the inefficient part. So look, the engine of your car is 30% efficient. These things are on average are about 10% efficient. These things, these ecosystems. Now, if you're thinking, why would environmentalists be concerned about that? Well, folks, it explains why there's a lot more plants in the environment than there are, in this case, tertiary consumers. I mean, think in your own experience in your life. Haven't you seen a lot more plants than you say grasshoppers? And you've certainly seen a lot more grasshoppers than rats, kind of depending where you live, maybe. And you've seen a lot more rats than you've seen bald eagles, haven't you? There's a lot fewer of them. The guys at the top are called apex predators because there's fewer of them at the top of the triangle. Now, where would we fit along here? Not with these organisms, but where would we fit? Would we be a producer or one of them consumers? Or higher, yeah. Or higher, depending on how big it gets, yeah. Could be. Forms what we call a pyramid of biomass, okay? And the reason why the pyramid of biomass and the pyramid of energy, when you put them together, are kind of neat to think about. This physics here, this loss of 90%, that's physics, not biology. But what that does is that affects the ecosystem. That means in the ecosystem, there has to be a pyramid of biomass. There has to be more plants than there are primary consumers. There has to be more primary consumers than secondary and tertiary and so forth. Yeah, for the most part, we usually are. There are a few weird instances in which, oh no, there's no documented cases in which humans are preyed upon. But there are some cases in which certain local groups of organisms, I'm thinking about crocodiles, alligators, have actually learned to exploit humans getting in the water. There's a place in India where the Indian monks, Buddhist monks, would go down every day and bathe in the river at the same time. And I guess the crocodilians there, or the alligators, one of those crocodilian critters, they all became used to that. So they would hang down by the river every day. So when the monks jumped in, they would, oh boy, feast. And since the monks were doing based on the religious faith, they couldn't change the time. So yeah, it's like feeding your fish. If you open up the top of your fish aquarium, many oftentimes to feed them, they'll swim to the top, won't they? Now, it also explains to, by the way, while you're thinking about that, well, it also explains to why it's a pyramid, why you get to the top, you can't have a lot of tertiary consumers, not a lot of energy up there. Okay, so now this whole transfer of energy never reaches equilibrium, okay? It never reaches a point where the amount of energy absorbed is equal to the amount of energy released. So that's what I mean by the energy in the Earth, or the Earth is not a closed system. I got a couple of other slides I need to go through before I return to this idea of a closed system, but I do put that in there in green, first of all, to kind of have you think about it first, but also because one of the arguments about the evolution of the universe is the fact that the Earth is a closed system, okay? And the Earth is not a closed system. Or the evolution of Earth and how that works on Earth, and evolution of organisms on Earth, arguments against it is that the Earth is a closed system. It's not a closed system. We'll see that in just a minute. All right. Okay, now I'm going to get into a little bit of theoretical kind of stuff. So I'm going to see if I can gently walk you through this. If you've had this stuff, then there's no gently walking through it needs to be done. But for those of you, including myself, by the way, who need to look at math in a very set, very confined way in order to understand it, I'm going to try to help you out with that. All right, up in the upper right, what that formula is telling you, the delta G, G is free energy, okay? It's called Gibbs energy, free energy. Think about free energy is the amount of energy that's available to do work, to do cellular work. Now, we'll talk about what all these pictures are showing you in just a minute. But you don't ever measure G, you measure delta G. And delta G is the change in free energy, okay? So we say that if the amount of free energy changes from point A to point B gives you a negative number, so negative delta G, means that the reaction is spontaneous. Okay? In other words, the reaction will occur all by itself. If I put a rock at the edge of a hill, it'll roll downhill by itself, right? Now, if the answer that you get, if the change in G gives you a positive number, so positive delta G, we say the reaction is not spontaneous. And you'll see in just a minute that there's another better word for it being not spontaneous. Now, spontaneous things, and I'm going to say something that seems silly, but I want you to focus on it. Spontaneous things occur spontaneously. In other words, they don't need the help of anything else. Non-spontaneous things don't occur non-spontaneously, so they do need help. All right, now this equation up above, so that's what delta G is, okay? And what we're saying is whether we can predict an equation, whether it's going to happen or not, by examining its delta G. If we calculate this delta H and delta S that I'll tell you about in just a second, and it comes up into a negative number, if the change in G is negative, then we know that reaction is going to occur spontaneously. And if that number is positive, we can say, nope, it's not going to happen. Those two things, those things that are going to react, you can sit there all day long and nothing's going to happen. Okay? Now, what is delta H? Delta H is the amount of heat that is absorbed or released during the reaction, and you subtract from that the temperature times the amount of disorder. That's what S is. S is the entropy. Okay, so delta H, yes, they can. That's exactly what they do. So now write this down for a second in your notes. So when we put all these terms together, if delta H is positive, then that means the reaction is endothermic. That means it needs energy. If delta H is negative, then that is ectothermic, and that means it releases energy. Okay, one more for you. If it's a negative delta S is entropy, negative delta S, Steve, not 2, that means that the system is less organized, less disorganized. And if it's a positive delta S, then the system is more disorganized. I'm not going to blow your mind with the math here, folks. This is really more a matter for those of you who've always kind of wondered how these equations relate. But now I'm going to try to turn this into the English language. I'm not going to have you calculating delta G's and delta S's on the exam. What this basically says is the amount of energy that any system has to do work. Okay, now this dude jumping off a diving board. Gravitational motion is energy. There's a natural tendency, spontaneous, for us to be attracted to the middle of the earth. The only thing that stops us is the earth itself. That's why when you jump off the board, you go down, you don't go up. There is a spontaneous reaction that occurs when molecules diffuse. We talked about that the other day in class. Now, the last thing, there is a spontaneousness to these large reactions, these large small molecules becoming smaller molecules. In other words, what's happening in the large picture is we're breaking down, say a glucose, we're breaking it down into smaller molecules. And when we're doing that, because of the way this reaction is set up, we are actually releasing energy. We're getting a negative delta G. So this is a spontaneous reaction, okay? So what we're looking at here is we say across the top, the guy on the top of the board, when the molecules are real confined, or when we have glucose, there's a higher G. Now, remember, you can't measure G, but it's the change in G that's important. But the system is less stable. The system is less stable because it's more organized. You see, stability and entropy go together. Stability and entropy go together. So this fact right here is tied to that. Remember, S was entropy. Mother Nature likes things to fall apart. The more disorganized, the better. Okay, so when these molecules are put together and confined together, they're less stable, and Mother Nature doesn't like that. So when the dude jumps off the board, he falls down. When those molecules are allowed to be released from diffusion, that's what they do. They spread out. And when a large molecule is broken down into smaller molecules, what that does is it increases the stability of the system. Maybe not of each molecule, but the system that all those molecules are in. Now, since that is a spontaneous thing that wants to happen, living organisms can make advantage of that. What they'll do is they can take that carbohydrate molecule, let it, or actually encourage it to break apart into those smaller molecules and release energy. You see in the little part where I put in the box, the system free energy decreases. Delta G is less than 0. And remember what I said, when delta G is less than 0, things are spontaneous. I said it at 10:02. Delta G is less than 0, it's spontaneous. Now, the reason why Mother Nature, the non-living part of this universe we live in, likes that or encourages that spontaneity, that thing to occur by itself, is because it increases stability. And remember, I even said that back early on when we were talking about atoms bonding together and ions. Why do they do it? Because it increases stability. Now, that releases free energy, energy you can do work. So if we go from the top to the bottom, when the guy jumps off the board or the molecules diffuse out or carbohydrates get broken down into smaller molecules, we go from a higher to a lower G. So delta G is less than 0. Dingo, spontaneous. I don't know why I said dingo, I meant bingo. Mother Nature gets what she wants. See, the right part of that equation is what paying the piper. If you want energy to do work, you got to pay this delta H. You got to pay this amount of energy that's released or absorbed minus the amount of disorder that you get or you don't get. And then temperature always influences this. Remember, temperature increases the rate at which these things happen, okay? So that amount of energy is released. Mother Nature gets what she wants. The stability increases. And, of course, the greater work capacity gets turned into less work capacity because energy was released. Back here, energy was released. When the guy jumped off the board, he released energy. When diffusion spread out, energy was released. When carbohydrate molecules, energy was released. Now, what do you think us eating those carbohydrate molecules do with that energy? What do you think we do with that delta G less than 0 that occurs because we broke down that molecule over here, this one, down into these smaller ones? What do you think we do with that energy? Well, we've already broken it down. But I mean, see, this is the physical part. What happened to the energy that was released when this happened? Yeah, we make it useful, don't we, Amber? What do we do with it? What's this bear doing with it? Kelsey, Mariah, Sadie, what's this bear doing with it? Colin. Yeah, it is because it's turning a lot of it into energy, but what's it doing with the usable part of the energy? What's it doing with the part of the energy, the part of the delta G, the energy that's released? What's it doing with it? I mean, some of it goes off in heat, yeah. Right, but what's it doing with a very small part of it? I understand, but what's it doing important for living things? The heat we give off is wasted energy. What about the energy that isn't given off as heat? What's that bear doing with that? Yeah, he's moving, right? It's kinetic. He's turning it into work, and inside of his body, he's building molecules. He's doing all these things that are necessary to keep living organisms alive, okay, to keep yourself alive. So you see, this over here, I keep wanting to draw my screen. This over here is a concentrated molecule. Mother Nature doesn't like those. There you go, Amber. And that means that molecule is going to spontaneously want to break down. And when it does, because Mother Nature likes things broken down, she doesn't like them together, it's going to release energy. Guess what? We're going to use it to our advantage. We're going to chase things with it if we're a bear. Or we're going to take notes about it. Okay, so I told you the words earlier were endothermic and ectothermic. There's another name for those. We call them exergonic reactions. Now, exergonic reactions and ectothermic reactions are the same. Ecto's on the outside. Exer is release, exiting. And exergonic reactions, the energy is released. Those are spontaneous. Okay? Look at the figure here. The reactants, where we're starting from, being turned into the products, the amount of energy decreases. Delta G less than 0. Okay? Delta G less than 0, the amount of energy is going to be spontaneously released. This is the amount of energy that we're going to use. Okay, only a little bit of it, but a lot of it goes off to heat, but the rest we're going to use to chase something down. Now? Okay, that's the spontaneous part. That's the Mother Nature part that she allows. Now, back to the other question. How did we get from here to here? How did living things turn these molecules that are apart to something that's together? What's the one thing they needed to do that? What's the one thing that they absolutely, to not disobey the laws of thermodynamics, do they need to do that? Okay, well, you got all the parts there. You got all the parts there. What else do you need to, Barbara, what else do you need to do that? Shaniqua, what else do you need to cause that reaction to go up the way it is in the blue arrow there? You need all the little parts, and then you're going to put those parts together. What do you need to put those parts together? You need energy, don't you? Okay, so this is what plants do. Plants do the blue arrow part. Plants also do the gray arrow part. They also engage, this is respiration, folks, they engage in that too. But anyway, only plants or photosynthesizers do the blue part. Where do they get the energy to do the blue part? Where do they get the energy to turn those simple molecules to go against Mother Nature, to actually cause a delta G that's greater than 1? Where do photosynthesizers get that energy from? Come on, folks. I want to hear from some of the rest of you. Isabel, Colin, Amber, Kelsey. Let's go. Yeah, they get it from the sun, don't they? The sun is a source of energy, the ultimate source of energy on the earth. Everything you are, everything you eat, it can trace its energy back to the sun. Now, the sun is not creating energy, but I don't want to go into how it happens. It's not violating the laws of thermodynamics, okay? It's just converting one form into another, all right? Makes sense? So it's spontaneous. What goes on in our body when we break down food and metabolize food and digest food is spontaneous. But we don't get a lot of energy from that. So here in a couple of slides, we're going to see how we sort of help make that a more efficient system, okay? All right. Let's go back to that open and closed system thing that I was talking to you about again. Eventually, what this looks like is everything would fall apart, right? If it were spontaneous, then everything would fall apart. And if you don't have energy, then you couldn't reverse the reaction that we just went through. Well, that's what I mean by the Earth is not a closed system. See, in a closed system, everything would reach equilibrium eventually. It's kind of like water pouring from a higher spot to a lower spot. It'll only do that until they're at the same level, right? Chemical reactions will being turned into B will only happen when everything has been turned into B. It won't go back the other way, especially if A to B is spontaneous, right? But here on Earth, we have what's called an open system. That's the sun. This spigot up here would represent the sun, to be honest with you. And it is putting energy into the system. And so we don't have to create energy. We don't have to violate the laws of thermodynamics here on Earth. All we have to do is rotate towards the sun. And every day when the sun comes up, it inputs energy in the system. So this keeps driving these reactions this way. Now, this is important because everything that has a beginning has to have an end. And I know you're trying to think, what does he mean by that? Energy has to move through a system. So what we've done, us living things, is we've just kind of inserted ourselves in here, to be honest with you. Right? We let the plants do this thing where they take the sun's energy and turn it into food, and then we turn that into, and see, we just sort of stuck ourselves into that open system. We kind of become one of those gears. That's why I always say all the time that biological organisms are fascinating, because they're really nothing more than this really awesome chemical reaction. And it's not like ionic bonds. It's this really incredible dance of molecules. Okay, speaking of molecules, I have to reintroduce you back to your buddy here, ATP. ATP was one of your nucleic acids. Now, if you forgot what ATP stands for, it stands for adenosine triphosphate. Okay, so here's a ribose sugar. Why isn't that a deoxyribose sugar? Here's a nitrogenous base. Why is that sugar there not a deoxy? Why is it a ribose and not a deoxyribose? And if you can tell me which carbon that is, I'll be very impressed. Do you erase all that stuff from your memory banks? Come on, guys. Jasmine, Jessica, Kelsey, Kyrian, Mariah. Wouldn't it be missing an oxygen right there? Is that truly something you all forgot? Or just... Hello, I haven't lost you all, have I? Somebody give me a thumbs up that they can hear me over there. I know I've got an alert that it's storming in Leesburg, so. Okay, so everybody is hearing me. Yeah, but you just didn't know the answer to the question? Okay. All right, so that's obviously not a deoxyribose sugar, is it? Because if it did, it would be missing an oxygen there. And that's the number 2 carbon, by the way. Okay, so this looks an awful lot like a nucleotide, but it's got 3 phosphates to it. And I introduced this to you back in the nucleic acids. What I want to point out now is the energy part to it. You see these bonds right here? Now, bonds are no different than anything else. To make a bond, to stick 2 atoms together, you got to put in energy. You're making something. Whenever you make something more complex, you have to put in energy. Whenever something more complex falls apart, it releases energy. That's spontaneous, okay? These bonds right here between the phosphate groups are very special. They're covalent bonds, but they're high energy covalent bonds. Now, why are they high energy? By virtue of the atoms that are sharing the electrons they are. Every time one of those bonds is broken, every time, here it is, every time hydrolysis occurs, energy is released. And there's even a number for it. It releases 7,300 calories, or 7.3 kilocalories per mole. Now, mole, remember, was we would add up all the atoms, and that would be the same weight of 1 mole in grams, okay? But now what I want you to tell me, why do I know, what can you tell me about those reactions that split those phosphates? What can you tell me about this energy that's released? Is it going to be released spontaneously or not? Look at the number up here and tell me. How do I know from this number whether that reaction is going to be spontaneous or not? This one down here. Yeah, it's negative, right? So that's a spontaneous reaction. That'll occur spontaneously. Those phosphates will we always say that ATP is unstable. Those phosphates are just ready to break off. It's almost like that tooth you had when you were a kid. Remember, wiggle, 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 and it was right there, right there. It didn't take much, and just finally pull it out. That's kind of how those phosphates are. They're like that wiggly tooth. So what's going on in your body here then is this. So we start over on the left-hand side. Okay, energy from catabolism. All right, now who remembers what catabolism is? What happens in catabolism? What happens to an atom? What happens to an atom in catabolism? Yeah, when an atom is undergoes catabolism, right? So look at this picture here. Like Amber says, what we're doing is releasing energy. When an atom undergoes a loss of electron, when electrons are moved, remember, we lose energy. So catabolism occurs during oxidation, right? Now, what happens then to the other word, anabolism? What's going on in anabolism then, over on the right-hand side? right? You're making it negative. That's what you're doing chemically, Amber. But what are you doing biologically? When you engage in anabolic reactions, think about what many of the baseball players have had troubles with, right? Anabolic steroids. What do anabolic steroids do? Do they make you smaller or do they make you bigger? Yeah, they make you bigger. They do make other parts of your body smaller, by the way, for you males. Just so you know, anabolic steroids have a nasty side effect. They make your testicles shrink. So it's up to you if you want to look that way. But anyway, all right, so back to the left, energy from catabolism. So in catabolism, you're releasing energy. You're releasing energy from food, right? So that yellow arrow on the left-hand side is going to be energy that's being released from food. And you're releasing that energy, and you're not turning it right into anabolic energy for cellular work yet, right? You got an intermediary. Remember I said these are like gears that turn. So the energy, oh man, I can't draw my screen. Keep trying to do that. The energy that's released from food turns a reaction that creates ATP. It sticks a phosphate onto ADP, folks. That's all it does. And of course, I just said the other way, opposite of the arrow I just drew, is spontaneous. So this is not going to happen here spontaneously, is it? It's not going to happen there. You got to have energy. Well, you get that from eating food. And then that reaction, that clock or that gear, I'm sorry, is going to turn a reaction that's going to be anabolic. All right? So we're going to turn reactions in which you need to build up materials. So it's got energies transferred first to ATP, and then ATP transfers that energy to cells. And the reason why we use ATP is common denominator. All cells speak ATP energy language. You don't have to worry about whether certain cells have problems using lipids for energy or proteins or carbs. Everybody uses, it's like in this country, if we all traded in different things. You know, some of you had gold coins, some of you had silver, some of you had marbles, and some of you had, you know, wooden sticks and straw. It'd be very difficult to have a common market there, wouldn't it? So you would want to have a common currency. That's why we call ATP currency, energy currency. Okay? Now, let me show you a very quick but awesomely cool example of how ATP does its job. Up at the top, what we're doing is we're taking glutamic acid, which is one of those amino acids, and we're combining it to ammonia to make glutamine. This is something that occurs in your body. I don't need to go into the detail because that's not the important part. But first thing, I want you to look at the delta G there and tell me whether you think this reaction would be spontaneous or not. Yeah, no, it's positive. I could put glutamic acid and ammonia in a bottle all day long and they're not going to make glutamine, okay? That's because that's a positive reaction. It's not going to be spontaneous. But here's what we do is we throw in ATP. And ATP has energy in it. Now, I'll do the math in just a second. That's what you're looking down below. But as I said, what ATP is, it's kind of an unstable molecule. And one of the things that ATP can do, when it breaks off that phosphate, that third phosphate, the energy that's released is going to help do the work that you see here. But that phosphate also attaches itself to the glutamic acid and makes it unstable too. So that phosphorylated intermediate, phosphorylate is just a fancy word for putting a phosphate onto something. Matter of fact, when you put phosphate onto ADP, previous slide, wasn't it? Yeah, you're phosphorylizing. This here is phosphorylizing. Okay, so when you phosphorylate things, you increase their instability. So when you increase things instability, what you do is you make it more likely that they're going to react. Okay, ATP is that, remember I said it's kind of like that loose tooth thing. So now you turn that phosphorylated immediate to kind of a loose tooth. And there's the ATP. And the ATP we'll talk about, you know, when we get to respiration. But what's going to do, it's going to be recycled. It's going to recycle that in your body. Now when you add ammonia, you can get glutamine. Now this will occur spontaneously, if you will. Not truly spontaneously, but it'll happen. So now in a bottle, if you have glutamic acid, ATP, and ammonia, you're going to get your glutamine. Now, the math behind that, okay? Up above, we said that in order to get glutamine, it takes 3.4 kilocalories per mole, right? And it was positive. Let's do the math down below. If you need 3.4, but every time you break off a phosphate, you release 7.3, then you can do the math. You actually have a surplus, don't you? So actually, an ATP molecule could catalyze or cause to happen 2 of these reactions, couldn't it? Because the net delta G, G is minus 3.9, so that's another spontaneous reaction that can occur. But you get the point of what's happening here? Up above, because of that positive delta G, that's never going to happen. But ATP, which is something only found in living organisms, can make the difference. ATP can lube the track so this reaction is going to occur spontaneously. And it does it by releasing energy and destabilizing things. In other words, it does them by making them wanting to react, by encouraging the reaction in this arrow to move to the right. Sometimes the action of the arrow is encouraged to move to the left. Sometimes not encouraged to move at all. So you're encouraged to the right. You're kind of priming the pump. Okay, now another thing that's going to help with chemical reactions, especially those chemical reactions which you have to make molecules, are these things called an enzyme. Enzymes are proteins. That's what that big blue thing is there. But like all proteins, enzymes have a shape. Okay, and even though that shape doesn't look anything like to you and me, that is a shape, right? But we call proteins what, globular shapes, we said they were, because they sometimes have a globular shape to them. But enzymes work on things called substrates. Substrates are the molecule that's going to be changed. But now there's what's called a lock and key arrangement. And what we mean by that is enzymes and substrates are specific. So enzyme A will only work on substrate A, and enzyme B will only work on substrate B. Actually, the best way to think about substrates is an enzyme only has one substrate. So you can't say that a substrate binds to an enzyme and nothing happens, because by definition, the substrate is the molecule in which something is going to happen. Later on in the lecture, I'll show you where things can bind to an enzyme that aren't substrates. And they do things, but they don't get turned into what we're going to see next called products. That's what you're doing this for. You're trying to turn substrates into products. So, of course, enzymes with their shape and substrates with their shapes are trying to be as perfect as they possibly can. But I love this part on the right. It always reminds me that Mother Nature keeps into fact the randomness of it all. Because it's what we mean by the induced fit model is if the active site or the substrate are close to the right shape, then everything is fine. They don't have to be perfect, but they have to be close to the right shape. Now, up above what an organic catalyst, I hope you know what organic means, right? Organic has a very precise chemical definition. But does anybody know what we mean by a catalyst? What do catalysts do? For example, this is a catalyst. This is pyruvate dehydrogenase. Oh, ASE endings are often referring to enzymes. Okay, but once again, what does a catalyst do? I always think about a catalyst as, yeah, speed things up, speed up reaction, or causes a reaction to occur. There you go, right. So the definition, organic catalyst, means that an organic molecule, carbons and hydrogens and all those complex, molecules and those shapes, because enzymes are proteins, because of its shape, it can speed up a reaction. And the reaction it's speeding up, folks, is turning the substrate into the product. Okay, so the substrate has to bind, and then the enzyme does some enzyme stuff, and what comes out is the product. And this is going to increase the efficiency. So even though glucose breaking down is spontaneous, these things, again, kind of add grease to the wheels. And this is one of the ones that we'll encounter when we actually get into respiration. This is a pretty complex one. This is called pyruvate dehydrogenase. Now, oftentimes, the name of an enzyme will end in ASE, and many times the name of an enzyme will tell you what it does, too. So pyruvate dehydrogenase is an enzyme that takes hydrogen, dehydrogenates pyruvate. So pyruvate is a molecule that we'll learn about here in a little bit, but you already know what it means to be dehydrated, or I'm sorry, to be dehydrogenated. It's your hydrogens are being removed off, electrons are being removed off, you're being oxidized, okay? I haven't told you before, but when we start moving into this idea of respiration and photosynthesis, that movement of electrons is usually always accompanied with a hydrogen too. So dehydrogenating something is also taking the electrons off of it. But the word is you're oxidizing it. So pyruvate dehydrogenase oxidizes pyruvate. And all the little pictures you see up above are all the protein makeup of it. So you can imagine the machinery and the mechanism it takes to put all this together. Of course, all the information that's in DNA to do that. And they even got pictures there. Kind of neat. The electron macrograph. Okay, so very simple in a nutshell. Here's how enzymes work. Start with number 1 up above. Substrates, they can be 1 substrate, 2 substrates, can be more than that. Anyway, whatever is going to start off is going to bind to the enzyme with a little help, right? Induced fit. And then that enzyme is going to work its magic, and what's going to happen is the substrates are turned into product, and the products are released to do their thing. And Mother Nature, being as clever as she is, recycles the enzyme. Okay, you can use the enzyme again. The enzyme is a protein. It's an expensive molecule. It took a lot of energy. It took a lot of amino acids to link it together to get that right shape. So you're going to use it again. You're going to put it in a cycle, and it's going to be like a factory. It's going to be turning substrates into products, substrates into products. See down below the general equation? Any enzyme and any substrate, and they're going to be specific for each other, is going to make that complex. And what's going to be released? The enzyme and the product. See, catalysts speed up reactions, but another part to catalysts is sometimes catalysts don't get changed themselves. Now, I gave you the reason why you wouldn't want to destroy the enzyme after one use. You know, it's expensive, like I said. It'd be like if you got rid of your car because it ran out of gas. But does that enzyme eventually stop being useful? Would you hypothesize, or would you reason that eventually that enzyme would no longer work? And folks, specifically when I mean no longer work, it would be shape, right? It wouldn't be able to accommodate the substrate. So would you think that would happen? Now, if you're trying to think, you know, what's he getting at? Remember what happens in the entire universe with something that's a system. Enzymes are a system. Just because you're not living doesn't mean you're not a system. What happens to all systems, folks? You're a system. What's going to happen to you? What is happening to you? Kelsey? They fall apart, don't they? Yeah, if they're living, they die. Isn't that right? They fall apart. So an enzyme will eventually fall apart, but you could get, you know, I don't know, several thousand, several 100,000 reactions out of it before it does. But again, the idea of destroying it after one would be silly if you think about efficiency. And, you know, I've mentioned that a couple of times throughout the semester. If you're in my Bio 2 class, I mention it probably every day. Living organisms are all about maximizing efficiency. It's why cells stay small. It's why you can use enzymes more than once, right? It's efficiency, so it wouldn't be efficient to destroy it after once. All right, now speaking of efficiency, the next slide shows you a graphical representation of what an enzyme does for a reaction. So let's kind of orient ourselves what we're looking at. Along the x-axis down here on the bottom, this is what we call the progress of the reaction. So we're going from reactants. Reactants and substrates are the same thing. Okay, reactants is what you would call them in a purely chemical sense, but in living organisms using enzymes, we call them reactants, but the same thing, okay? And then on the right is products. And on the y-axis is the amount of free energy. So remember, we want to go down the graph. We want to go from higher to lower if we want it to be spontaneous. Okay, so if we want the delta G to be negative. All right, so let's take a look at these two plots. Let's go with the black one first. So the black plot says that if you plot the free energy of a system going from reactants to products, you find out that first, kind of confusingly in a little bit, that you need energy at the beginning. right? This is what this is showing. This said that delta G is positive, and delta G being positive means that it's not going to be spontaneous, but that once you get up over the hill, then it'll fall through spontaneity. Okay? Now, if you want to be efficient in all of this, you're hoping the amount of energy that was put in is less than the amount of energy that you get out. Right? That makes sense. It's like investing. You're not going to invest $1 to get out a nickel. You're going to invest $1 to get out $2. Okay? So what this hill is that I'm talking about, it has a name for it, E sub A. It's called the energy of activation. So it's kind of, think of it as the amount of energy needed to prime the pump, to get it started. So this might be the amount of energy that it took for that kid to roll that slide up the hill, right? You got to pay a little. The trick is for efficiencies, do you get more out than you put in? And you do here, okay? But without the enzyme, you need X amount of energy of activation. But with the enzyme, you can see in the red, you need a lot less, don't you? So what enzymes do is they take these spontaneous reactions and they help them occur at a much lower cost, right? Because these reactions that are going to occur, something's got to break them apart. So there's going to be a lot of energy involved in a living organism that's going to have to be invested to obviously get, as I said, if it's efficient, more energy out. You're going to want to hope that that's going to happen. I think that's like the old myth or legend that it takes more calories to chew up celery than you get from it. I don't know if that's true or not. It might be. There's not a lot of calories in celery, but that would be an example of using more energy than you're getting. Well, just if you were losing weight, it's the same thing, eating less and exercising more. All right, now you probably shouldn't be too surprised by these next few slides, but this involves homeostasis again, right? Back to homeostasis. And if you're thinking, well, what does it mean homeostasis? Regulation of enzyme activity, right? That's all homeostasis. You can't have enzymes turning things into products 100 miles an hour all the time. You have to have ways to slow it down. You have to have ways to speed it up. You have to have ways to control it. It's kind of like when I was trying to teach my daughter how to drive. It was very hard for her to understand that you didn't have to have the accelerator all the way to the floor to go, that there was a variable speed car. I think she learned it a few times after a few speeding tickets, but nonetheless, right? It's the same thing with enzymes. So let's take a look at these 3 different ways that we can regulate an enzyme activity. Now, you only see 2 on the screen. I'll introduce you to another variant, really, but another way. All right, so on the left is normal binding. There's the enzyme. There's the substrate. They fit. Everything's fine. Okay, big deal. In competitive inhibition, what happens is another molecule. It's not the substrate, because, again, only substrates get turned into product. But the blue molecule there, that competitive inhibitor, it will bind to the active site, but nothing's going to happen. It's not going to get turned into product. It's not going to destroy the enzyme. But what it's going to do is it's not going to allow the substrate to bind. Now, the substrate and the enzyme, they don't stay bound forever, but neither does the competitive inhibitor. So after a while, the competitive inhibitor would disconnect. And then there would be that competition again, depending on who gets there first. If it's substrate, you get product. If it's another inhibitor, then you get inhibition. Now, it's a little different in non-competitive inhibition, but it's still the same idea. A molecule, this time it's what, orange, down at the bottom, binds to an area that's not the active site. There's actually a name for the area. It's called the allosteric site. That part where the orange molecule is bound, it's called the allosteric site, okay? So that doesn't stop the substrate from binding, but it changes the shape of the active site, you see? And when you do that, then you can't have substrate binding. Okay, now, the regulation thing. It's real simple, folks. Look, with competitive inhibition, if in an environment there are more competitive inhibitors than there are substrate, then the reaction is going to be favored that you get inhibition. If there's 1,000 competitive inhibitors, 1 enzyme, and 1 substrate, it's probably going to be a competitive inhibitor probability-wise it's going to bind. And that's the same thing with the non-competitive inhibitor, folks. So cells change the numbers of those 3 quantities. They change the number of substrates. They change the number of competitive and non-competitive inhibitors. They might change the number of enzymes. But all that is places in which you can kind of regulate, stabilize, and maintain, that even keel that you want with enzyme activity. Now, one final thing, and I'll go on from here. In non-competitive inhibition, if the substrate binds first, then the non-competitive inhibitor can't bind. If it binds first, then the allosteric site's shape gets changed. Not cool. All little molecules doing their dance. Okay, there are also things that are called allosteric activators. There are molecules like the one in the green there that when it binds to the molecule actually stabilizes the enzyme. So this particular enzyme is pretty complex because it's got 4 active sites and molecules are movable around. So maybe you think about the activators being the drill sergeant, right? Everybody in line, and that means you have those active sites shaped, stabilized, and you're going to increase the reaction. And then inhibition, same thing, right? You can an inhibitor that doesn't necessarily change the shape of the active site, but it destabilizes these molecules. So it makes the active site kind of move around and bounce around. So the variety of ways you can bind to the active site, you can bind to the allosteric site, you can actually increase stability, you can actually increase instability. And that's going to, all of those are going to add into the reaction. And then finally, this is really cool. You can actually have a binding of a substrate that increases the chances that other ones are going to bind. That's what happens in hemoglobin. Hemoglobin binds oxygen, right? So, and you can never have too much, well, you can have too much, but you want to make sure you can carry as much oxygen as you can. And so every time an oxygen molecule, that's the substrate here, every time it binds to a hemoglobin, remember hemoglobin was 4 proteins, that actually increases it changes the shape of the active sites. So the induced fit model here would imply that hemoglobin is really flexible about the fit. But once you get a fit, then the other ones become very nicely fit, and you increase the chance that that hemoglobin will bind. Any questions on that so far? Where are we? Oh, good, we got time. Now, as you probably can imagine, chemical reactions and biological reactions aren't as simple as A to B for the most part. Most of the times, chemical reactions occur through a variety of steps like you see here, right? Sometimes it takes 4 enzymes to get that final end product. So you have these intermediate substrates, or it could be called intermediate products too, because like for enzyme number 1, intermediate substrate A is its product. But think about it as building a car on an assembly line, right? You don't put it all together at once. You have to put it together in little pieces. And notice where these are located too. They're on that phospholipid bilayer, right? Lots of important enzymes on that membrane. All right, now this situation where you have an assembly line of materials being made allows us to talk about the last type of inhibition. So we got competitive, we've got non-competitive, and this last one is known as feedback inhibition, right? Feedback. Now, feedback doesn't involve anything binding anywhere special differently, but it involves, well, it throws it into more realistic context. It throws in this thing I was just showing you, the slide earlier. And what happens in feedback inhibition is we say that an excess of the final end product, and that's an important word to keep in mind. It's the excess of final end product. The excess of the final end product can act as an inhibitor. Okay, so let me show you what I mean. Over on the right, we have an enzyme known as threonine deaminase. And if you're thinking, well, that must take maybe an amine group off of threonine, you'd be exactly right. That's what it does. It's an enzyme. And anyway, it takes, what, 5 enzymes to get the final end product, which is isoleucine. So that's the purpose. You're turning threonine into isoleucine. The cell needs to be able to do that, okay? Now, if the cell called up for, let's say, 1,000 isoleucine molecules, once you reached 1,000, there would still be all those intermediates kind of in the works. So there would be, what we might call a chemical inertia. You know, like when you're pushing something and you stop and it keeps rolling. So even though you reach 1,000 isoleucines, all these intermediates in these enzymes are going to keep working. So you're going to overshoot 1,000. You might have 1,100, let's say. Well, the 100 are excess, and that's the key. The 100, see the red arrow, go back and bind to the threonine deaminase enzyme. They bind at a different spot, so they bind to an allosteric site, and they inhibit the enzyme. And so if the enzyme can't bind to threonine, you don't get any of the reactions. Now, if you want to turn it back on again, if the cell says, hey, I need another 1,000 isoleucine, there's 100 already sitting right there because those are the excess. Well, the cell will grab those 100. There's no excess. There's no inhibitors. That's why it's called feedback inhibition, right? In this particular case, this is what we call negative feedback because the end product increasing, okay, is actually going to increase the negativity of not making any more. So the more you increase, the better your chances are of not making any more of your cells. So the more isoleucine goes up, the better chances you're going to shut down the enzyme. Okay, I've just got a few slides I want to go through with you. We'll finish this up. I think we'll probably get through this chapter today. I don't remember if I have it scheduled, but it has to finish today. No, I have a little time. What chapter is this? This is 8. Yeah, I got a little time Monday, but we'll run to the end anyway. Okay, now let's talk about how the environment affects enzymes. And this isn't going to take much, especially when we get to the second 2 slides. But the first one really isn't going to take much either. Enzymes have an upper rate. Okay, so along the x-axis is how much substrate you're adding. And on the y-axis is, how fast it's happening. And like anything, right? Like my daughter driving her car, like you running, like you working, an enzyme is subject to this idea that eventually it can't go any faster. And in this case, it's, somewhere where the blue arrow is just after 51, whatever that concentration is. All right, so enzymatic reaction is going to increase as you add more and more of the substrate and the enzyme together. That makes sense. If you add more gas to the engine car, you go faster. But eventually you reach a saturation point. You reach a point at which the enzyme can no longer go any faster. Okay? So we would typically expect in an enzymatic reaction increasing rate and then a leveling off. Any questions on that? Okay, enzymes are proteins, so they're also affected by things that can, oops, hold on. There we go. They can be affected by things that cause denaturing. For example, hold on a minute, there we go. Temperature can denature an enzyme. Now, at first it's good because remember when you speed up molecules, they move faster, and an enzyme and a substrate only bump into one another at a chance. So the faster they go, the better you increase that chance. But eventually up around, 37 degrees, you denature the enzyme and the reaction rate drops. So they might be moving a lot faster, but because they're denatured, they're not working. Okay, folks, one more slide and I'll stop, okay? So this is about denaturing. Now, saturation is not about denaturing. It's simply about saturation. This is about denaturing. This one is about denaturing. Little different shaped graph than the temperature one because we don't have this speeding up of the reaction, but we have an optimum pH for this enzyme at 4.4. And pH is another thing that'll denature proteins, and enzymes are proteins. So as you move away from that optimum pH, it doesn't have to be 7. The ones in your stomach, the proteins, the optimum is 2 because that's the enzyme of your stomach. But as you move away from that, the enzymes are denatured and the reaction stops. Okay? All right, folks, I'm sorry I ran a minute over, but I'll stop there. If you have any questions, by all means, stay online and we can discuss that. If not, you all have a good and hopefully dry weekend. Keep eye on the website, and I'll let you know if classes are canceled, and I'll see you next week. Remember, number 5, I will provide. Do not print off number 5.